Hello, this is William from PCTE, and today I'm going to be doing a presentation on using phase detection or phase analysis of ultrasonic pulse echo results to determine if a grouting duct in a precast panel has been correctly filled. Now, this presentation is an expansion of a written article we created last year, which looked at a number of different sonic and seismic tests to investigate if the grout was voided in these precast elements. This is a specific expansion of the ultrasonic pulse echo example, and it looks at grouting in the grout duct region as opposed to between the precast wall elements. Ultrasonic pulse echo is a technique you can use from a single side of a concrete element. It uses shear wave energy, and its most basic incarnation is simply recording the time of transit of a pulse of shear wave. Now, it is very common to combine multiple sensors into an array, as you can see in the top right picture there. That is Proceq's Pundit PD 8000 array. And these produce a tomographic image. That is, they give a representation of the concrete structure, sort of a one-to-one presentation. So we can see here on this step cast slab, there is sensitivity to the voids, which are just essentially a cast-in pipe, and the bottom of the concrete slab. Now, the conventional presentation of ultrasonic pulse echo data with tomography is to look at signal strengths. So in the previous example I've duplicated here, a weak signal strength indicated by a light blue color was the energy over a duct with void filling grouted correctly, and the voided slab was a stronger energy, represented by a orange or red color here, showing a stronger signal strength. Now, in order to do this evaluation, the settings of the Pundit array that took the data had to be kept all the same gain and signal processing, so that the two results could be compared. Now, the examples I'm going to present today are data post-processed in Proceq's Pundit Vision Software. This was previously known as Intersaft and has been developed by the University of Kassel. It allows reconstruction of Pundit data or other ultrasonic pulse echo array data, and particularly it allows the combination of several scans into a 2D or 3D image. But the particular subsystem I'm using today is the phase visualization and evaluation, which is an alternate way to represent this data. I need to quickly explain what phase is. So when we talk about the phase of a waveform, it represents a particular position along a periodic waveform. So on the right-hand side, we have a sinusoid, sine wave, and the phase is illustrated from 0 to 360 degrees, or 0 to 2 pi radians, along the whole cycle of one waveform, one wavelength. So 90 degrees at the most positive and 270 at the most negative. When you transmit shear wave energy, or sound wave energy as well, into a physical structure, and it's reflected back towards the transmitter and received again by a sensor, there will be some shift in the phase, as illustrated here. So the signal reflected back to the sensors has had a slight difference in where it arrives. So if we compare the waveforms, there is a phase shift shown here. We're evaluating that phase shift of shear wave energy trying to distinguish an air boundary to a solid boundary. So that's a grouted duct to an ungrouted duct. And the reason that we evaluate phase rather than evaluating the signal strength or heat map presentation or amplitude presentation is the settings become a little bit less critical. When you are comparing amplitude or signal strength, the gain and all the settings need to be kept fixed, whereas when you're evaluating phase, there's some scope to make adjustments to get the best visual presentation of the data and then compare the phase to evaluate a grouted to ungrouted region. It also removes some uncertainty. If you were able to detect a duct, but there was little difference in the amplitude or the signal strength, it's practical to compare the phase shift and see whether that indicates the grouting status. Now, when we're looking at the upcoming examples, I'll be presenting a phase wheel, which you can see in the bottom left corner here. This is a presentation of what phase shift was experienced by the shear wave that was sent from the Pundit array into the concrete element and then reflected back from the duct or the bottom of the slab or somewhere else in that concrete element. Practically, there will be a number of indicator arrows coming from the center of that phase wheel to show the phase shift. Also, the particular presentation of phase wheel that I'm using here goes from 0 to 180 in a positive direction and 0 to 180 in a negative direction, depending upon if it's going counterclockwise or clockwise. So we don't go all the way through to 360. We look at the phase shift in terms of how much out towards the 180 mark. Now, just before we begin looking at data from grouted ducts and ungrouted ducts, I want to look at a single B scan and evaluate the shear wave energy in that B scan. So in particular, a single measurement was taken over the grout duct, and we can see, as in the drawing, the rebar with full grouting, unvoided grouting, and then the bulk of the concrete material. On the B-scan presentation, we have a signal from that duct, and we have a signal lower down from the bottom of the slab. The interface between the grout duct and the concrete is a solid interface, and the grout duct and the interface between the bottom of the slab and the air underneath is a air boundary. So we should see when we compare the phase shifts that there will be a difference. So let's begin by comparing the phase shift at the grouted duct. It's a reflection at a solid interface. So the phase shift here is 101 degrees. So we can see that just going up into the purple region of the phase wheel. Then when we look at the phase shift from the reflection from the bottom of the slab, we can see we've got a number of different colors in there, but it's somewhere between a orange and a green result. And you can see all of those different results in the red box or the black box. And the average is minus 119 degrees of all of those. So I have now put together the phase wheel and images from the grouted duct and the bottom of the slab. So we can see them on the left-hand side, 101, on the right-hand side, minus 119 degrees. And comparing the two phase wheels, it's not a perfect 180 degree difference in the phase shift for the grouted duct versus the phase shift of the air interface at the bottom of the slab. It's 220 degrees, but there's a clear and quantifiable change, which could be used to tell the difference between the two interface types when comparing the data. We can now begin looking at data collected over a completely grouted duct and compare it with data taken on a duct before it was grouted, so a fully voided duct. in this particular example, this is the grouted duct. Now, because the geometry is over the entire length of that duct, we now have what's called a C-scan presentation on the right here, in addition to the B-scan. So the way this works is this red line shows the depth of 60 mil, into which the C-scan is a top-down presentation, or sort of into the surface of our wall panel. So we've mostly captured the phase shift occurring in the top half of the grouting duct, and that colors are purple, so roughly 90 degrees signal. And going a little bit deeper to 90 mils into the wall elements, we're catching primarily the phase shifts occurring on the bottom half of the duct, and it's now a red signal, so a 180 degrees. So our signals for the grouted duct, the filled duct, are somewhere between 90 to 180 degrees in the positive direction. Now, taking the same measurements over an unfilled duct, the geometry in this case limited the ability to place the array only to the top half of the duct. So the C-scan on the right is half the height, but we have in this case a phase shift result into the green section of the phase graph. So somewhere between -45 to -90 degrees negative phase shift is the result on a completely empty duct, a duct to which that no grouting has been completed. So we can compare our two results now, and we can see that the phase, the average phase is between the two 90 to 180 value. Call it positive 135 for the completely filled duct, the duct with successful grouting, compared to, call an average of -67 degrees for the empty duct. So again, there's a quantifiable variation, grouted duct to empty duct, of around 200 degrees comparison between the two phase shifts. So this is the completion of the case study, just looking at the way that phase evaluation can differentiate the interface between an air interface and a solid interface, particularly in the context of grouting ducts and precast panels. It's been a pleasure to speak with you, and if you've got any more questions or would like to try this application on your projects, PCTE have demonstration and trial equipment and the ability to work with you to test some data through the Pundit Vision Software, and we'd be very happy to show you some more on this technique or to try it out on your projects. Thank you very much.